Thank you, Musio. Thank you for the organizers for inviting me to this great workshop, and for Peter for swapping with me and doing a great job with an overview on samarium B6. I have really 5 years worth of data, and hopefully I'm going to get the message across. And I do realize that I'm the only thing between you and lunch, so hopefully you can stay with me and I won't give you an indigestion at least. So in the first part of my talk, I will discuss recent experiments on samarium B6, and recent I mean from the past 5 years. And I hope I get to go to part 2, where I'm going to introduce this new material we have been working on that is a possible non-symmorphic topological insulator candidate with a giant negative magnetic resistance. So I couldn't have done this work by myself. I have a long list of really great collaborators here at Lano: Sean, Joe, Philip, and Vivian. Vivian at the High Magnetic Field Lab. At UCI, Zach and Jing, and this is really where all this started when I was there working with Zach. At the University of Michigan, Kurdak and Jan did a great job with the double Corbino disk measurements that I'm going to show. I have 2 pieces of scanning tunneling microscopy data, one from Stefan Werf's group and the other one from Mohammed and Jenny. And finally, recent ESR electron spin resonance measurements that John and Pascual performed in Campinas. So let me give you a one-slide introduction on samarium B6, now from an experimental point of view. So samarium B6 crystallizes in a cubic, simple cubic lattice with a lattice parameter of 4.13 angstroms. Unfortunately, we're going to see that there's nothing really simple about this material, although the lattice is very simple. So if we look at the periodic table, here the boron cage takes exactly 2 electrons to perform its covalent bonds. If we have, for example, calcium, strontium, or barium, which are divalent hexaborides, then we have an insulating ground state. Perfect, right? Minus 2 electrons, plus 2 electrons, you get an insulator. But now if we have lanthanum, cerium, praseodymium, or neodymium, which are 3+ lanthanides, then we have exactly 1 electron per unit cell. We have a metal, a very good metal actually. Lanthanum B6 has beautiful quantum oscillations. What about samarium? That's when things start to get complicated. Samarium is neither divalent nor trivalent. It's actually somewhere in the middle. From X-ray absorption spectroscopy, we see that the valence is actually 2.6. So this is a mixed valent compound. So what is it going to be, an insulator or a metal? I would say a metal in principle because we have more electrons there. But no, resistivity shows a really nice insulating behavior that increases by 5 orders of magnitude. So how do we explain that? And I thank Peter again for telling us about the hybridization that is important to understand the insulating behavior of this material. So the 4F band hybridizes with the conduction bands. And we can understand this by looking at the periodic Anderson lattice model. So here we have our D electrons, our F electrons with some Hubbard repulsion, and to hybridize with a hybridization strength V. Okay, so now we can say we are starting to understand this material, and you think also we know what the ground state is, but actually it took 40 years for X-ray measurements to determine the ground state of this material. And that's partially because neutrons or neutron scattering would be the way to go, but there's a lot of absorption problems in this material. And very recently, really early this year, Severin's group was able to determine the ground state, which is now a gamma 8 quartet. Okay, so now we can say, oh, we understand this material, we understand the ground state. We know that this high temperature part is due to F electron physics. But what's happening here? What is the saturation doing here? Yes? Well, yeah, this is a picture problem, but the ground state is the gamma 8. So, okay, what's happening there? So there is in principle, the first thing you have in mind is that this is due to impurities, and that's what earlier work thought that was due. But recent theory work by peers and collaborators show that maybe this material is a topological insulator. So one can calculate the topological index by calculating the parity at the high symmetry points and show that this is actually, depending on where your Fermi level is, one can get a weak or a strong topological insulator. And in fact, D bands and F bands have different parities. So if they mix at some point, then you may have here the opening of a hybridization gap. And if your EF is between those two bands, then you have an insulator, a topological insulator, and therefore surface states have to be present. And 5 years ago, there were two experimental papers that actually were able to see the presence of surface states in this material. So in this case, there is Hall data as a function of thickness. And below about 4 Kelvin, which is where the resistance plateaus, the ratio of the Hall effect goes to 1, meaning that it doesn't depend on the thickness of the sample. You always have the same thing because it's the signal you're seeing is proportional to the surface, not the bulk. But the question that remains is whether the surface states are topological if they have spin texture. And I can answer you right now. The answer is maybe. It's not yes, it's not no, it's maybe. The second question I want to answer, and Peter also talked about this, is whether the quantum oscillations are coming from the surface or the bulk. So there was the first report was in 2014. Here, the authors claim that the quantum oscillations observed in SmB6 are coming from the surface, and that's due to a two-dimensional 1 over cosine theta dependence of the frequencies. And this also showed that the oscillations come from light effective masses. It's very, very important to keep in mind that there are two different samples out there. The first one is grown using flux-grown method, and that uses samarium and boron in a 1:6 ratio, so a stoichiometric ratio, but a lot of aluminum. And why? Because aluminum is a low melting point element, so we can heat up the solution to, let's say, between 1450 and 1550 Celsius, and we have a supersaturated solution that we can start cooling down to form the crystals. And you say, why aluminum? Well, aluminum is fairly good in dissolving boron, which is a really hard task experimentally. But we still need a lot of aluminum to dissolve boron and make this supersaturated solution. So that aside, these are the data. They see torque magnetometry data using a cantilever, and they're beautiful oscillations that start at really low fields, actually 5 Tesla. And they also did angular dependence, and they see 3 pockets. The first one is really small, around 40 Tesla, and it's very noisy because it's hard to get the intensity from the FFT at such small fields. But anyways, there are other 2 pockets that have a 1 over cosine dependence. And here is their list of parameters, but I wanted to show or point out that the effective mass is very, very small. It's only 0.1 of the effective mass of the bare mass of the electron. And a year later, there were reports of 3D oscillations coming from SmB6. But again, it's important to note that these samples are different. They're grown by the floating zone method. So in this case, we don't have flux. We only have a polycrystalline seed. And you can use, for example, a xenon lamp to heat up that polycrystalline seed and move the sample away from the focus to start growing the single crystals out of the polycrystalline seed. It's important to note that one has to go to really high temperatures to melt the polycrystalline seed, and this is above the boiling point of samarium. Anyways, they could see oscillations using the same technique. And what's intriguing here is that at low temperatures, this does not follow the normal Lifshitz-Kostević formula. And on the other hand, the amplitudes here of samarium B6 and rotating magnetic field are somewhat similar to those of praseodymium B6. So many questions there, but which one? Which one is correct? And I can also give you the answer right now, and unfortunately I think the answer is neither. But let me show you why I think that's the case. Okay, so what Sean did was to use a cantilever as well, so same technique to measure torque. And here you can see, for those of you who know PPMS, this is just to be used in a PPMS, so much simpler, I would say, to lower fields. And here is just the cantilever, which is a copper foil. So we have a really nice big sample here. And indeed, we do observe the HVA oscillations in the torque of this samarium B6 sample. However, we only saw oscillations in about 50% of the samples. So you can see that here in S2 and S4 we see oscillations, but S1 and S3 we do not. And the lack of oscillations here correlated with how thin the samples were. So we started polishing the samples, and here's what we found. There are 3 unconnected aluminum deposits here. And you think, you may be asking yourself, is this a smiley face, or is the crystal being sarcastic? I don't know. Sometimes it's hard to understand what nature is trying to tell you. But I think this is a smiley face. Anyway, so we polished the sample again, trying to get rid of the aluminum, but it was still there. There was another deposit hidden in the bulk of samarium B6. And what was interesting is that both these samples have oscillations. And if you scale the torque with the mass of the sample, the oscillations are on top of each other. So although the aluminum deposits, they are kind of randomly oriented, and it's not really homogeneous at first, actually they are on average the same in the volume of samarium B6. And you may be asking yourself what this yellow line is, and that's when we polished the sample to 1.5 milligrams, and we found no aluminum deposits, so the oscillations were gone. You can do the FFT of this data as well. Yes? I'll get there in the next slide. Yes, again, next slide. Yeah, you're absolutely right. We're only going to 13 Tesla here with a normal PPMS. I'll get there in minutes. So we can compare our FFTs to polycrystalline aluminum, and we can see that we can see only a couple of frequencies, especially in the second one, the polish 1 sample. And this is because, unfortunately, aluminum co-crystallizes with the samarium B6 cubic structure. They're both cubic, and their lattice parameters are really close, like to 2%. And again, we can do the angle dependence, and it fits very well 1 over cosine theta, which is the dashed line. And we also compare our data to Larson's data. So Larson measured aluminum in 1967, I believe, and the data really is on top of his measurement. Well, there's a little bit of a difference here, but we think it's because of this small mismatch between samarium B6 and aluminum, there's a little bit of strain that may change the frequencies a little bit. But the effective mass is 0.1, the bare mass of the electron. Okay, and then, wow, so the referee, not happy with all this, asked us, oh, what happens if you try to measure SDH, which is oscillation and the resistivity. And no one can see them, and I'll explain it to you in a minute. But if you polish the sample and attach leads to the aluminum deposit, then the SDH oscillations show up. So we can see that here. And the dingo temperature is 10 Kelvin, which is 1 order of magnitude larger than that of pure aluminum. And that's because we have impurities in the flux trapped in the aluminum. And so the dingo temperature is larger because the mean free path is a little smaller. Okay, so to your question, Piers, actually, Lou Lee had magnet time in Tallahassee, and he took the same sample S5 that I just showed you that doesn't have any oscillations to 13 Tesla. And there are no oscillations to 45 Tesla. And I think that's enough, unless you want to go higher than that. So to 45 Tesla, there is no sign of quantum oscillations. There's a little bit of hysteresis here, and we don't understand why that's the case, so we're still investigating that. So we need really a bulk-sensitive probe. Here's resistance versus temperature and resistance versus field, and there is no sign whatsoever of the superconducting transition temperature of aluminum. And that's because, you may remember, below 4 Kelvin, the transport in this material is dominated by the surface. So most of the current flows on the surface, and therefore, we cannot see whether there is an aluminum inclusion inside, deep inside the bulk. So we need a bulk probe, and in this case, AC susceptibility is able to see HC. Here is AC chi versus field, is able to see HC of aluminum. So this is very unfortunate to my, as far as I understand, but I do think the community needs to know about these results. And we are trying to think if it's possible to make a more general statement, because there are two types of sample in the literature. These results were in flux-grown samples, but you may ask yourself what's happening with the floating zone samples. So let me try. So here is the most recent report on floating zone samples, just from earlier this year. And here they tried to plot the quantum oscillation frequency as a function of rotating angle for both flux-grown and floating zone samples. So circles are floating zone, and everything else is flux. So you may see here that in the bottom, there are only flux-grown samples. And then you may wonder, well, is this aluminum or not? Because from what I mentioned before, it is. So let's compare this part of the graph with aluminum. So the black squares are from this paper, and the red and blue squares are from two different reports on aluminum, one from 57 actually, sorry, and the other one from 1978. And I think it's pretty clear that they match. For the second rotation, again, the same thing happens. And now you may be confused because I showed in the beginning floating zone results with low frequencies that are not shown here. So let me show you that to you again. So here's SmB6 in a floating zone sample. You can see that below 1,000 Tesla, there are many, many oscillations here that are not shown here in the newest paper from the same group. So I'm guessing they just forgot to add those frequencies. Right. I have no other explanation. So what's happening then? We know that all these frequencies here, unfortunately, are coming from aluminum. But you may be asking yourself, what about the very high frequency ones? And unfortunately, again, I have to bring up disorder. And the fact that there is a very recent paper by Lian Fu and Shen, also Peter mentioned that briefly. And here in this case, they start with a very simple model with a Hamiltonian that has two bands and here electrons and holes that are hybridized. So delta here is the hybridization. They can include disorder in this Hamiltonian with an impurity potential here, U. So when the disorder is larger than a critical number, which is roughly of the same order of the hybridization gap, they see that the imaginary part of the self-energy has a diagonal component here, which is proportional to the scattering rate of the quasi-particles on the D bands and on the F bands. So if you have disorder in a strongly correlated system, you can calculate what the spectral function is, and you see that there are oscillations that arise in the system, even though the system is still insulating. And this is consistent with our previous results on bulk AC conduction that do see that there is something there in the bulk, and also the residual heat capacity that Peter also discussed. So there are localized in-gap states that are able to give quantum oscillations in this material. Okay, so on that note, let's talk about DC transport. So Kurdek and Jan did a fantastic job preparing these Corbino disks. So let me walk you through it. Here is a side view of that disk. So here in the middle, there is one disk. You can see here this golden disk. And then there's a second one, which is this guy here. And then the third one, which is the outer one. And then finally, the fourth one is the whole thing. So if you want to do a standard 4-probe measurement, you can apply current between the inner one and the outer one, 1 and 4. And you can measure voltage here between 2 and 3. Then you have a standard 4-probe measurement that we're used to. However, one can think of an inverted resistance measurement. And here, if you still apply current between the inner and the outer one, all the current, if you are in the surface-dominated state, will be flowing over here. So if you measure along 5 and 6, what would you expect? The contribution from the bulk. Because although you are in the surface-dominated regime, there must be some conduction in the bulk still. And that's the inverted resistance measurement. And you can do some calculations and show that in this regime, your resistance will be inversely proportional to the resistance of the bulk. And that's exactly what they measured in the stoichiometric samarium-B6 sample. Here is the standard method, is the curve I showed you before. It increases and it plateaus, but the inverted resistance drops because it's inversely proportional to the bulk resistance and keeps going up. However, if we try to add disorder to this material by growing samples with samarium vacancies, the resistance starts to drop, but then it plateaus. So if we plot the resistivity versus 1 over temperature, we can see for the stoichiometric sample a 10 order of magnitude increase in resistance, which is just mind-blowing. However, if we start including vacancies, or removing samarium, then we see a plateau here. So the first thing to note is that for all the samples, the activated gap extracted from this graph is the same. So there is no change in the bulk activated behavior, no matter what you do to the sample. However, there is a little bit of saturation here, but this saturation is fairly high. The resistance is fairly high. So we think it's unlikely, and we couldn't fit it to a variable range hopping mechanism, but we do think that maybe if there are low dimensional defects that percolate, this could give rise to the saturation here. And that's where STM comes. And Stefan and Lin Zhao try to understand or investigate the role of magnetic impurities on the surface states of these materials. And so in a sample with 0.5% gadolinium, they started on top of the gadolinium impurity and they went away from it. And here on the DIDV spectrum, right on top of the impurity, there is no signature of the surface state peak at minus 6.5 MV. But as you go away from the impurity, so scans 2, 3, 4, 6, etc., then the surface state component starts to show up again. So they can see this intensity rising and pretty much plateauing at 2.2 nanometers. So it's like you have several gadolinium impurities in your crystal, and they all have a range where they really locally suppress the surface state. And when they overlap or percolate, then you may start seeing this in other measurements. And just to note that 2.2 nanometers is not that big. It's about 5 unit cells. So you just need really 3% of magnetic impurities to percolate in your lattice. And that's exactly what we see in resistivity. For small concentrations of gadolinium, there is still a saturation here. But for 3%, the resistance keeps rising. There's another piece of evidence I wanted to share with you. All this was done with a non-magnetic tip, tungsten tip. But if we try to use a magnetic tip in our experiments, then the surface state peak is also gone. So this may be taken as evidence for spin-dependent surface states, although I must say that this is very indirect. And finally, for the electron spin resonance, so gadolinium is a very, very good ESR paramagnetic probe. So we can add gadolinium to the cubic lattice, and we can investigate what that does. And here at very, very small concentration, we see Lorentzian lines, which are indicating that the environment around gadolinium is very insulating. But as we increase the amount of gadolinium in the sample to 0.4 and 2%, then we see somewhat lines that are somewhat not symmetrical, meaning they are Dyzonian, not Lorentzian, and this is an indication of a metallic environment. And if you want to know more about this, I'm running out of time, please visit Jean's poster. I won't have time to talk about this STM result. I will just mention that Mohammed and Jenny were able to focus their quasi-particle interference or measurements inside the gap, and they see that in the X point, there is a dispersion there that has a very large effective mass, which is consistent with thermoelectric power data from 2015. So the take-home messages are, there are no quantum oscillations in stoichiometric flux-grown samples. We show that by polishing the samples. The bulk DC transport of SmB6 is robust, although there are localized in-gap states. Gadolinium impurities destroy the surface state locally and percolate above 3%. And there are in-gap surface states that appear to have heavy electron masses. So in the 1 minute I have left, let me talk about the second compound, because I really wanted to show you this data. And this is motivated by theoretical predictions that non-symorphic materials may have surface states, particular surface states, that have spin polarization. So this could be a 3D analog of the spin Hall effect in 2D systems. And this barium-5, indium-2, antimony 6 compound was predicted to be one of them. And we wanna see 4F analogs exist. So I grew nice single crystals of the europium analog, and it's orthorhombic. Here's a crystal structure. And it has two magnetic transitions, one at 14 and one at 7. Up to here, it's a normal europium compound. Here you can see the heat capacity anomalies. However, transport is interesting. So it is very insulating. The resistance goes from 6 ohm to 310 to the 6th ohm. So 6 orders of magnitude increasing resistance, which already is crazy to me. So if we apply magnetic fields, there is a really giant negative MR that arises. This is 99.99997%, which is also, to me, by itself, very interesting. And you may be asking yourself what this is, and this is nothing but the field-induced transition. Here, in the transverse MR, we can see that transition very clearly at lower temperatures. And the combination of europium moments, low carrier density, and large MR near the nail temperature is screaming to me that there are magnetic polarons in this material, but we're still understanding what's happening, and Pascual has now samples, so hopefully ESR can help us with that. So I would like to finish by making an advertisement. I'm looking for students and postdocs, so if you like this type of work, please contact me, and this is my email. So thank you. Thank you.